will help you understand how fine resonance works in area quant software. First of all, I'm going to put the software in simulate experiments mode because I don't have an instrument actually connected, and it's a little bit easier for me to explain how the fine resonance program works in this mode. The first thing I'm going to do is load the simulation instrument file, which I do like that. It comes with every version of software that is delivered to our customers. And for reference, I'm using software version 0.8.3. So in order to understand how fine resonance works, it helps to be in diagnostic mode. So I'm switching to diagnostic mode now. So the first thing I'm going to do is a quick start and capture a single pulse FID. So in this experiment, a single pulse FID is applied at the resonant frequency that the instrument believes is the correct frequency. And you see here a decaying sinusoidal exponential. You see that there's a real and imaginary component associated with these waves. So what happens when the instrument's acquiring data is the oscillating voltage that's produced in the measuring coil is compared with a reference voltage, a reference wave, and the real and imaginary components are extracted. The relationship with respect to phase of the real and imaginary components isn't important for the purposes of this exercise. Now, one of the things you'll notice is that there are several periods associated with the oscillating portion of this wave. That means that these data were not acquired at the resonant frequency of the magnet. And if I click on live data here, and then click on this icon, the power spectrum or the Fourier transform of that, I see the Fourier spectrum of these acquired data. And what this shows me is that the resonant frequencies offset by about 2.8 kilohertz. And I can see that by placing the crosshairs on the peak of that FFT spectrum. In the upper right-hand corner over here, I will see the X and Y coordinates. So if I do that, I see that the X coordinate is minus 2.8, meaning that the resonant frequency is shifted about 2.8 kilohertz from the actual resonant frequency of the magnet. Now if I go over here, I can see that the resonant frequency that the software, the frequency that the software applied the RF pulse at was 13.507 megahertz. Now, if I go in here and I select Find Resonance, and I click Start, you see that the instrument has applied an RF pulse that's offset from the resonant frequency it believes is correct. So if I just click Stop here for a minute, you see that the offset from what it believes is the actual resonant frequency of the RF pulse is 1 kilohertz, and it's constructed a series of 21 different values. Now, in the software, when we were performing the measurement, trying to find the resonant frequency initially, these steps are a lot bigger. We start off with 10 kilohertz steps, and then after a sweep of all 21 data points is produced, then we go back and refine that step to 1 kilohertz step. So I'm going to let this continue, and you're going to see that this peak here in the Fourier transform is going to slowly move towards the actual resonant frequency. As that happens, you'll also notice that the number of periods in this captured wave will decrease. Let's watch that. So you see this is shifted over 1 kilohertz. When we're exactly on resonance, the peak of the power spectrum, or the Fourier transform of the data, will be exactly there. see that the number of cycles in the echo that we observed, the free induction decay, is decreasing as the peak in the power spectrum is moving closer to the actual resonant frequency. And if we look over here, you see this behavior here, that we're going to see a sharp peak in the component integral at the resonant frequency. If you look down here, you see that we're on the 10th data point, and if this table were expanded, that 10th data point is going to be back here at 13,507. See how the number of cycles is dramatically reduced. So qualitatively, you can look at the number of cycles in the free induction decay and estimate how far off you are from resonance. So the integral, the RMS integral, if we took these data points, we squared them and then took the square root, we'd get this curve here, this magenta curve, which we call the modulus of the echo. And you see that's a positive function. If we turn off the, let me just go back here, if we then turn off the free induction decay, the real and imaginary components, and just look at the modulus of the echo, if we take the area under the echo, that gives us the value that we're looking at here, which is this blue curve, the root mean square integral of the free induction decay. So now, if we go back and turn this on, one of the things that you'll notice is if you get very far from resonance, you'll have no echo whatsoever. So you'll see that the root mean square will be a very small number, and the only value that you will in fact have is the number that's related to the inherent noise in the measurement. But as you get closer to resonance, you start to see the behavior that we observe here. If I go back here and look at this red curve essentially looks at the number of times the real and imaginary components cross the x-axis. And you can see that when you're far away from resonance, the number of zero crossings will be large. When you're at resonance, the number of zero crossings will be very small. So if you look at the reciprocal of that, you'll see this component integral with this very sharp peak at resonance and then becoming very large as you get relatively farther and farther away from resonance. So that's how we find the resonance frequency. And when you're doing measurements, it's very easy to do a simple FID with the verification liquid. We typically use a recycled delay of 400 to 500 milliseconds. And in a few scans, so let me just do that here. So in the course of 5, 6 seconds, it's very easy to see how far you are away from resonance. Now, the instrument has this fine resonance fine-tune feature. And the difference between that fine resonance fine-tune and the ordinary or the usual fine resonance algorithm is that fine resonance will work when you're far away from the resonance frequency. Specifically, you can be up to 100 kilohertz away from resonance on either side, either in the positive or negative side, either less than the actual resonant frequency or greater than the resonant frequency, and still be able to determine the resonant frequency. This fine tune only works over a relatively narrow band, about 35 kilohertz, either plus or minus from the actual resonant frequency. Fine resonance will fine tune the applied RF pulse to exactly the resonant frequency on the order of a few cycles. And it does that by looking at this offset of the Fourier transform peak in the power spectrum relative to 0. And that may take 2 or 3 cycles. So we can do that measurement simply by clicking this here. So it's a little bit quicker than find resonance, but accomplishes the same objective. One of the benefits of the fine-tune algorithm is when we're using find resonance, it will find the resonant frequency within 1 kilohertz, up to as much as 1 kilohertz away from the actual resonant frequency. A fine-tune will, in principle, determine the resonant frequency down to about a hertz. Now, that's not going to stay for very long, but may be sufficient in terms of capturing the best data.